Wow, we could hear a pin drop in here. It's so quiet. Thanks for coming on such a nice day. So we're going to start the last unit today. This is on clustering and some related approaches. So let's first talk about what is clustering. So clustering is another one of these unsupervised tasks where you are given a set of feature vectors, but that's it, no labels. And your goal is essentially to create labels for them. We call this clustering. Basically, you want to partition that data set into K groups where samples are similar within a group and different across groups. So as an illustration, you're given this data without any colors, and your goal is to put those colors on there. Your goal is to say, oh, I think all of these are related to each other, and then all of these are related to each other, and so on. There's some variations of these algorithms that for difficult samples, they will tell you, like, I just don't know how to categorize those. I don't know how to cluster those. But you can see that clustering is, in some cases, clustering is maybe kind of easy, but in other cases, it's more difficult to see how you would do this because, for example, two of these blue points here are much farther apart from each other than some of these blue and red points here. So it's not, just about measuring the distance between pairs of points. There's more to it. Okay, so basically, but that's the goal. I'm going to partition the data set into K groups. Is that pretty clear? Okay, so so we'll talk about a few algorithms, but the one that's probably the most famous, the most common, is called K-means. And the goal here is to design K-centroids. The centroids are the center of each of the clusters, essentially. And in particular, you want to minimize this cost. So this cost is a little bit funny looking. We have seen a lot of costs throughout the semester, and we have seen like we want to minimize a cost. So you often see min of the cost, but this cost actually has a min inside the cost. I don't think we've seen that before. So the way to interpret this is, so the cost is over C. That's what we're trying to design, are these centroids. We're given the data xi. And this says you should design the centroids so that the closest centroid to xi has a minimum distance. So I didn't say it too well. Basically, the cost is the sum squared distance from each sample to its closest centroid. So that's the idea. So as you move around these centroids, which one is closest to a given sample will change. Okay, so to understand this maybe better, once these centroids are designed and you want to use them to cluster your data, you just look for which of the centroids is closest to your ith data point. So that's just basically like doing this min, but let's do an argmin. So we'll actually capture the index k, and we'll call it kappa. So that would be the cluster label. And if you think about it, these decision regions are just Voronoi cells. So like if the pluses tell us where the centroids are, then all the samples in this region here, everything in here will be closest to that centroid here. So no matter any sample that's in there or any test sample would be classified or categorized as belonging to that centroid. And then similarly, anything over here would be categorized as belonging to that centroid, and so on. So we are trying to design where to put these things so that the sum squared distance is minimized. Okay, so that's what k-means is trying to do. Any questions on that? Is it making sense? Okay. So it turns out that this is a really difficult cost function. It's there's really no algorithm out there that can minimize it perfectly. Except for some like exhaustive search. So basically, in practice, what you do is you use an approximate algorithm called Lloyd's algorithm, which is the most famous one to solve this problem. It's quite an old algorithm, and it's very simple. It just iterates 2 steps. And so let's say we're given some initialization of the centroids, maybe a very bad one, and then we're just going to iterate these 2 steps. Given those centroids, you compute you figure out what is that Voronoi cell, and you just compute the sample mean of the data within that cell. Then, now that you have the new sample mean, you just set the centroids at those sample means, and you repeat. So here's how it looks. So here's our data we're given, and let's say that this is our centroid initialization. We have the blue centroid and the red centroid. So the first thing we do is we do the Voronoi cell, which is just going to be the line that bisects those 2 points. So it means everything on this side belongs to blue, everything on this side belongs to red. And so that's what's shown here. Everything is colored appropriately. And now we just take the sample mean of all the blue points. That gives us this x here. And the sample mean of all these red points gives us this x over here. And so those are going to be now our new centroids. And we repeat. So with those new centroids, we again get the Voronoi cells. And then for all the samples in this cell, we compute its mean, which ends up being over here. For all the red samples, we compute its mean, which is over here. And once again, based on these, we can get the Voronoi cells. And we keep doing this. And you can see, it looks like it's converging. At some point, and going from here to here, none of the red and blue points change teams. And so that means that the sample means are identical. And as soon as you see the sample means identical, nothing is going to change from that point on. So you just terminate the algorithm. Okay? So basically, you just alternate these 2 steps. Compute the sample mean within the Voronoi cell and set the centroid at the sample mean. Okay, so that's this practical algorithm. Any questions? Yes.
How do you decide the number of?
Oh, the number of classes?
Yeah,
or,
just right.
yeah, that's a great question. A lot of these algorithms you have to tell it in advance. There are some that are able to, there's some that are able to try to guess that, and then there's even if an algorithm doesn't try to guess it, there's ways that you can add like a model order selection kind of penalty to it, and then you treat it as a model order selection problem. But this particular one, yeah, you got to tell it exactly how many centroids you want. Sometimes you know that, and sometimes you don't. Okay, any other questions? Okay. All right, so like I said before, this cost function that it's trying to minimize is not something that we can analytically solve, or it's not like a convex problem or anything. So we can get stuck in a local minimum. And that can happen with Lloyd's algorithm. So there's basically 2 main improvements that have been made to this. One is a careful initialization. And there's a famous approach called k-means plus plus. So this initialization is still sort of random, but it has certain guarantees. And that definitely helps, but it doesn't solve the problem. It doesn't mean you won't get stuck in a local minimum. It just means tends to be better than a random initialization. And then the other thing you can do, and you can do this with k-means plus plus, is you can just use a whole bunch of initializations. You do this over and over and over again, and you compute, every time you compute the value of this cost, and you just choose the initialization that gave you the lowest cost. So those are two things in practice that you can do to make things better. All right, so, okay, so that's actually all we'll say about k-means. Any last questions about k-means? Okay. All right, so now let's talk about a motivating application, which is document clustering. So imagine you're given a collection of documents and you want to organize them. You don't really know how the documents differ, but you think maybe they can be clustered into similar categories, like maybe these are documents about sports or documents about science or news or whatever, and you want to try to figure that out automatically. So that's the goal. And this is an example of what people sometimes call text mining. We haven't really dealt with text yet, so this is another motivation to look at this to see at least one way of dealing with text. And for our demo, we're going to use these Usenet articles. Usenet is like a really old online discussion forum. Started in the late 70s, peaked in the 90s. And the reason this is nice for machine learning classes is because the documents are pretty simple, pretty short. There's not that many of them. Also, there does exist ground truth category labels or classes. So when we try to figure out, we try to predict these labels ourselves, we can compare them to some truth and see whether we did that well or not. Okay, so so this 20 news groups data set contains data from 20 different Usenet categories. So these are the categories. So you can see it's kind of hierarchical. There's a bunch on computing, there's a bunch on recreation, science, and so on. And each of these categories has about 1,000 documents. And the documents are not very long. They're sort of email length. They look a bit like emails. We'll see one in a moment. This is built into scikit-learn. And we'll just load 4 categories. And this gives us, for the 4 categories we loaded, there's 8387 samples total. And the ones we're going to look at are alt atheism, computer graphics, science, space, and talk, religion, miscellaneous. So just kind of looking at these categories, do you think that these are going to be easy to cluster or not so easy to cluster? So I see some, Jack, why do you think not so easy?
So I feel like the alt atheism and the talk religion could have a lot of overlap.
Exactly,
And even some
yeah.
of the space stuff, you could theoretically think that has religious ties into it, especially with the names of planets, depending on what religion.
Okay, yeah, that's interesting. But yeah, I agree with the first thing you said. Definitely there's going to be a lot of overlap between these, so we might not be that successful in separating those, but maybe these other ones are different enough that we can separate them out. So we'll see. Okay, so so in terms of how the data is loaded, there's this dataset object. There's a data field, which contains an array of strings that are the posts. And then there's also a labels field that is the categories of the posts. So it's kind of like just the targets, if you will, that we're trying to recreate without knowing what they are. And then also the titles of those categories. And here is an example of a post. This is the code, obviously, and then this is I think this is just the post right here. You can see it's quite short, looks kind of like an email. And this is from computer graphics, so it's someone with a video card asking for help, how to get their card working. Okay, so that's the data we'll be working with. And the first question is, well, how are we going to work with strings? We don't really know how to do that yet. So, so we're going to use something called the bag of words model. So this is a pretty famous, pretty well used model, but as we'll see, it's not super powerful. So the way it works is that you look at all the different documents in your corpus of documents, and you write out all the words in all the documents, like you kind of build a dictionary for all your documents. And the words are always called terms, not words. And for each document, the way that you represent the document is just as an array of word counts. So as an example, very simple example, imagine my corpus has these two documents. So I take all these words. Oh, I forgot to mention, you omit common words like the and so on, because those are not going to be very useful. So here's the list of those common words. They're called stop words. So whenever you see any of these, you just throw them out. Any other words, you add to your dictionary. So here's a dictionary for all the documents. And now the way I represent my documents is document 1 is just a vector of counts in my dictionary, and document 2 is this other vector. So this is such a small example that the counts are either 0 or 1. General, that's not going to happen. But here, these documents are so short, and they're different enough that either a word is in one or the other, but not both. But in general, you can have maybe the word is appearing in both, or the word is appearing twice in one and once in another, and so on. Okay, so what are some of the pitfalls of this model? Can anybody think?
Reduce some notion of order in the words.
Yeah, there's no sense of ordering at all. It's just like, that's why it's called bag of words. So it's like, this has a lot more information in it than this vector here. But the idea is that for some tasks, maybe this is enough. Maybe this is all you need. Not for everything, certainly, but for some of these simpler tasks, maybe that's enough. So nowadays, when people are training these large language models, obviously they're not doing this. They really are focusing on the sentence structure, but this maybe is from an earlier generation where we had simpler techniques, simpler models, and we weren't going for that level of structure. Okay. All right, so we still have a couple issues to solve, which is that some of the documents could be much longer than other documents, which makes them sort of difficult to, compare directly, or makes the vectors difficult to compare. One is has a lot more ones than another, a lot more terms than another, and then some of the terms themselves are much more common than others, and that that should be significant, but maybe we want to modify how we're encoding things a little bit to take these two things into account. So that's where we get this particular way to construct features called TF-IDF features that tries to get around these issues. So, so rather than working with this representation directly, it looks at what's called term frequency. So this is the ratio. This is something you compute for every combination of document and term. This is the number of occurrences of that term J in document I, divided by the number of terms in document I. So as you can see, this is going to be a number that it's going to be less than 1 in general. In the extreme case, the document has one particular term and only one term in that document, then you could get all the way up to 1. But this is basically normalizes for a given document. It normalizes the value of each term, somewhere between 0 and 1, and we can think of it as a term frequency. Okay, any questions on that? Okay, so the second thing is this inverse document frequency. So if we look inside here, inside the log, you can see we have something, we have a ratio of number of documents with term J over the number of documents. So if you fix the term here, you can see that terms that are very common in many documents will have a larger value here. Terms that are very unique, like to one document, will have the smallest possible fraction. And since that's sort of inversely proportional to how important that term is, you want to focus on the terms that are important. They will be the rare ones. You actually want to invert this ratio. So it turns out if we have a minus sign outside of a log, we know that that's the same as moving the minus sign in is like inverting this. So that's where we get this inverse document frequency. And it happens to be better to put this on a log scale. So there is also a log there. So these are these two sort of different features, and the way that they're combined is you just multiply them together to get the final TF IDF features, and you basically construct your feature matrix with those. So this is a matrix where as you go down the rows, you go through the different documents, and as you go across the columns, you go across the different terms. Okay, so even though this is quite a simple model, as of 2015, it was used by 83% of the text recommender systems. So it's definitely a very common thing to do. And just as a note, the way that we're constructing this matrix in this class is consistent with the way we've always constructed our X matrix, but if you look at most of the literature, it's transposed. Okay, so anyway, this is what we call the term document matrix. Okay, so this is how we're going to process features. We get these documents, we build these kind of raw features, and then we, from them, build these more sophisticated things, and now we finally have some features we can use. And once we have these, we can just treat them. We can use k-means or whatever else we want to use on those vectors. All right, any questions? All right. Okay, so let's talk a little bit more about this term document matrix. Okay, first of all, how could you use this? In addition to clustering, the document retrieval problem is basically kind of what a search engine does, except minus all the wanting to give you advertisements. Ideally, what a search engine would do is you have a massive collection of documents on the internet. You type in a term, and you want the search engine to tell you which documents are most related to the term you typed in. So if you have this X matrix, you can do that by just extracting the jth column of the matrix. So that is specific to that term. And now you have a vector over all the different documents. And the higher the number there, the more important that document is to that term, at least according to the way these features were constructed. So it's exactly what you would want to do like for search. Something else you could do is called semantic analysis if you want to find the relationships among different terms. So you might want to say, essentially you're saying, like, I have a whole bunch of documents. How often is technology and machine learning, how often do they appear together? Are they related or are they not related terms? And so what you can do there is you again extract a column, in this case for each of the terms, and now you just compute its inner product. You compute this. And the larger this is, the more connected those two terms will be. These are just some examples of what you can do once you have this term document matrix. Okay, all right. We're going to use it for clustering. Any other questions? Okay, so a few other important things about this matrix is that it tends to be huge. So even if with our really simple demo, where we have like 3,300 of these Usenet articles, we end up getting 38,000 different terms in our dictionary. So that's a lot of terms. So if you think about how big this is like 40,000 by, 3,000 or 4,000. So that's a pretty big matrix. Well, it turns out that most of the entries in that matrix are 0 because most of the documents don't have every term in your vocabulary. Because like if we have 38,000 words, but only 3,000 documents, 3,300 documents, there's no way that all these could appear in every document. It's like less than 10% of them will appear in a document. So that means you're going to have tons of zeros in this matrix, and we call that a sparse matrix. A sparse matrix is just a matrix where tons of the coefficients, or a big fraction of them, are 0 value. So a lot of computing frameworks have ways of dealing with sparse matrices, representing them. So rather than allocating memory for every element in that matrix, you just allocate memory for all the non-zeros. You basically make a list of all the non-zero elements in the matrix. You have memory allocated for each. And then you have another list of where in the matrix those elements appear, like the coordinates. So when you have a really sparse matrix, this can save you tons of memory as well as computation. So that's how we would want to represent this, is as a sparse matrix. There's other important properties. This matrix tends to be low rank, or nearly so. This can be exploited for document clustering. Also, the matrix is non-negative. All the terms are non-negative. So this can also be exploited, as we'll see. Okay. So how you do this TF, IDF stuff in Python or in scikit-learn, it's super easy. You just instantiate this TF, IDF vectorizer. You tell it what language you're working with. It has an official list of stop words for that language. And then you just take that array of strings and you do fit transform and you get your X matrix. Simple as that. And here we're printing out the dimensions, which is, as we would expect, 3387 documents, 38777 terms. Now that we have this, we can just run k-means on that term document matrix to see if we can cluster documents. So, any questions? Okay, so we'll do that in a moment. Let's first take a look at the scores we've computed. So let's take one of the documents. Let's take document number 10. And let's look at, so that document is basically, the way we're representing it is, this is a vector of, 38777 entries, right? All those entries are corresponding, each one corresponds to a given term. And this document only has these terms in it. For all these other entries, you see the TF-IDF feature is exactly 0. That term does not appear in the document. So these are the terms that appear in the document, and you can see the feature values are here. So basically, this particular word is, you could say, is the most important word in that document in terms of making that document special within the corpus. Okay. This is actually the same post we saw earlier where the guy was looking for help with the
So
card.
one quick question I have, so how would it recognize the differences like between colors, like the English way and the American way of spelling? Like how would it differentiate that? Or would you have to like manually program in differences like that?
Well, I mean, they're not stop words, so it would just treat them as different words.
So even if they have the same meaning, they were meant to be used in the same way, it would recognize it as two different.
Right, exactly. But if you did something, like if you had a corpus that had, English and American text, and you did something like this, you would see a very high correlation. You'd be like, oh, you might even be able to recognize that those words are synonyms. Yeah, so that information is kind of encoded in the representation. Okay, so so this is how this document looks. It's just this long vector of values. Most of them are 0. Okay, so now that we have this, we can run k-means. So here's an example of running k-means. So you have to tell it here how many clusters you want to use. So, we know we're going to be looking for 4 clusters because we know we created our data set from these 4 different documents. We're going to initialize with k-means ++. We're going to run this for 100 iterations at most. Usually it will stop before that point. We're only going to come up with one initialization, only one random seed. We're not going to do this a bunch of times. And it prints out for you the value of the k-means cost at iteration 21. It stopped. And let's see what happens. Okay, so let's think, what does k-means give us? K-means gives us a centroid. In particular, it gives us 4 centroids. Each one of these centroids is similar to a document. It's 38,000 long vector of TF-IDF scores. And each of those scores corresponds to a particular term. So what we can do is we can just look at, for each of these centroids, we can look at the top 10 TF-IDF scores. So centroid 0, these are the top 10. Centroid 1, these are the top 10. Centroid 2, these, and centroid 3, these. So what do you think? How successful was it just based on looking at the centroids? Do you see some correspondences there? So it seems like at least this one is very space-like. This last one looks like pretty good match to computer graphics, but the first two, definitely they have some, okay, this one definitely has some religious terms in it. This one, that's hard to say. Could be kind of anything. And these are our categories. We had atheism, computer graphics, space, talk, religion. Okay, so rather than just looking at these centroids, we can be a little bit more precise in analyzing this. We can build a confusion matrix where we have, we kind of imagine that we are trying to guess the true labels. These would be the true labels. I'm trying to guess them from the features, even though for training we never saw any examples of true labels, so that's how this is different from classification. And so we can compute the confusion, print the confusion matrix here, and we're going to normalize the rows. Let me see, or is it actually? I think actually the columns might be normalized. Yeah, I think. Yes, I changed the code last time, but I didn't change this. column normalized. Okay, so that means for each of these clusters, we can see the spread across the true classes. Okay, so let's start on the right. So for cluster 3, this is great. 97% of the samples are coming from computer graphics. So it did a really great job of isolating that. For cluster 2, 99% are coming from SciSpace. So that was also successful. Cluster 1, 67 or 61% alt atheism, 39 talk religion. We said that those are pretty difficult to separate, so maybe that's also successful because there's almost nothing from these other classes. So we can maybe say that's kind of successful, but this one, you can see this one didn't work at all. It's almost uniform across those 4 true classes, so 3 clusters were good, the last one somehow didn't work. Okay, so that's what we get with k-means. Any questions there? Okay, let's take a look at one of these errors. So even though this is really good, let's look at one of the let's look at one of these errors. So this is the actually I think it's this whole thing. This whole thing is the post. And what you notice is that the color red and color are used a number of times. And so even though this was from alt atheism, because of the use of that word, it seems a lot like a computer graphics post. So it kind of makes sense that this is why this was categorized as computer graphics. Okay. All right. So that's k-means. Any last questions on k-means or document clustering? Okay. So let's think about some other ways of doing things. Can we solve this with PCA? So it might seem kind of strange. What does clustering have to do with PCA? So as we know, what PCA does pictorially is something like this. So this is our term document matrix, a matrix where we know as you go down the rows, you index over the documents. As you go across the columns, you index across the terms. And we also know that what PCA does is essentially does an approximation that takes the form of a singular value decomposition where you force the rank, this is the economy SVD, you force the rank to be R. R is this thing we choose, right? Like in this case, we'd be choosing R equals 4 for the, because we know we want 4 classes. So this would be an approach. And the reason why it works is it's sort of like, if you think about what this means, if you force this dimension 4 PCA approximation, you're basically saying, I'm going to say that X is of this form. Because this is a rank 4 matrix, it basically says all these different rows all live in a subspace of dimension 4. I mean, at least according to this approximation. So even though you have capital N different documents here, well, really they're all just vectors in this 4-dimensional subspace. They all have that in common. Meanwhile, if we think about each term as being, in this case, represented by a vector of these counts across documents, even though we have D of these terms, where D is very large, 38,000, by applying PCA in this way, we are essentially forcing all those guys to live in some 4-dimensional subspace. And what is this thing that there's only 4 kinds of documents, there's only 4 kinds of terms? Those would essentially be the topics, right? Sort of forcing this approximation onto your data, saying there's only 4 ways you can make a document, there's only 4 ways you can make a term, according to this. So this is how we can connect PCA to clustering. Whether this will actually work is another question, because it could be that for r equals 4, there's no way to get anything close to an approximation here. So you end up maybe getting a very bad approximation. So yeah, so maybe this just does not give you anything close to the X matrix, and therefore it might just fail. You're trying to like squeeze something with a lot of complexity into these 4 buckets, these 4 topics. Maybe that's too much. So we'll see. But I think conceptually it's kind of important to understand how PCA can be used in this way. Any questions on that? Okay, now there's this variation. It's kind of a slight variation. It's new. It's called non-negative matrix factorization. So the way that it's very similar to PCA in that you're also coming up with a rank capital R approximation of X. You're not doing it with an SVD. In particular, you're saying, I want to come up with the W and the H matrices that minimize RSS, just like PCA, except I need them to be non-negative. So remember with PCA, there's no non-negativity anywhere. When you run this SVD, you're going to get positive and negative terms for U and V. You will get non-negative S's, but the U's and the V's will be pluses and minuses. Here, when you do NMF, though, non-negative matrix factorization, you get non-negative W and H. So you're putting this extra constraint on it. Because there's an extra constraint, you're not going to fit the matrix as well as PCA will fit it, because you're trying to do everything PCA is doing, plus you're saying, oh, and by the way, you can't give me any negative values. So it has a harder task, and it gives you a different answer. It's a little bit more difficult to solve for NMF. I think I have a slide on this. Yeah, we'll talk about this in a moment. But again, conceptually, we're doing the same thing. We're essentially saying this term document matrix, somehow all the terms or all the documents in there should live in an R-dimensional subspace, and all the terms should live in an R-dimensional subspace. But moreover, there's going to be some positivity. The reason we can exploit positivity is because X is positive, or X is non-negative. If X had negative values, then you're not allowed to do this. You just can't do it. But because this is non-negative, we have the option to try to also force these to be non-negative. And we'll see that there's actually something really interesting that happens when we do this. It's quite different than PCA. So we'll talk about that in a moment, but let's try to run both of these techniques on the data. Okay, so we run. Oh, and I forgot to say, when you run PCA on the term document matrix, it is called latent semantic analysis, just a terminology. Okay, so when we run PCA on this, this is what we get for the confusion matrix. These are principal components 0, 1, 2, 3, the true classes, and you can see that none of them are very great. These two are the best, but they get less than 70% as compared to K-means got like 99. Right? And then this one is just pretty bad. It's almost uniform between them. And this one, okay, this is similar quality to K-means, where it's about half and half. But, so it kind of works. Not quite as well as K-means, but actually, it's not absolutely terrible. Kind of worked, surprisingly maybe. Okay, so this is PCA. Any questions on this one? All right, so now let's talk a little bit more about non-negative matrix factorization. Okay, so for NMF, I think I said all this. This is the cost function, it's RSS, but you have these constraints that W and H, in addition to them being, tall and wide matrix, they are non-negative. The main advantage is that the coefficients are more interpretable. Larger means more relevant. Meaning, if you find like near zero value coefficients in W and H, you can interpret them as saying, that topic is just not that important to that document, or that term is not that important. With PCA, it's more difficult because you have positives and negatives, and how do you interpret a negative versus a positive? It's just not quite clear. But with NMF, it's more clear what you're going to get. Okay, so NMF on 20 news groups. Let's see how it works. So we basically have, again, two good clusters, 93%, 85%, so pretty good. Not quite as good as k-means. But when we look at the other remaining clusters, both of them are pretty decent. They're splitting those two categories pretty well, and they're not polluted by these other two. So, whether this is better or worse than k-means, maybe not exactly clear. K-means did have that one category that was just, that one cluster that was not really getting anything. At least here, all the clusters seem to be making sense, although none are quite as clean as for k-means. Okay, so that's NMF. Let me tell another story. So have you guys ever heard of the Netflix problem? So the Netflix problem was about, I don't know, maybe it was 2010-ish. Netflix made a contest. I think they gave $1 million to the winner, and it was a lot of money, whatever it was. And they had a matrix, giant matrix X, where along one axis you had movies. Along the other axis you had, movie individuals. And within the matrix, you had movie ratings. But the challenging thing with the Netflix problem is that a given person has not viewed all the movies on Netflix, right? So there's some ratings here for that movie, or let's say, okay, so a given person has watched a few movies, but most of the other entries, most of the entries are just like question marks. Like, they're not zero. These are movie ratings. They're not like, if you haven't seen it, it doesn't mean you don't like it. You just don't know what the rating should be. And then the other way too, for a given movie, only some subset of the people, Netflix subscribers, have seen it. So there's a lot of question marks. And so there too, the objective for Netflix, or for the contest, was to figure out, essentially to fill in the gaps. So Netflix would like to give recommendations to you about movies you haven't seen. So you're a column, so then it wants to fill in all the gaps, say how much you will like these movies. And one way to do that is, once again, non-negative matrix factorization. You just solve this problem, which essentially says, except what you do is, so for any entry for which you don't know, you don't include it in the Frobenius norm. So you just take the sum squared across the entries that you have data on. But otherwise, you solve this problem. You can do it iteratively. And that wasn't the absolute winner of the contest, but it was the main ingredient in the second method, or a lot of methods had that ingredient. So it's quite a powerful method. It has uses beyond clustering. And with one example here too, we can understand it from the perspective of this, the face experiment. So these are different pictures than we saw on Friday, but let me try to explain. So these here are the eigenfaces. So these are the eigenvectors, each one of these squares. This is the mean. And then these other ones, I don't know exactly where they start. And this is on a different data set than the one we saw in the last unit. But these are the different eigenvectors. And then these are the eigenvalues. And I don't know exactly the color scheme here. I'm thinking that black is high and red is low, but I'm not 100% positive. So basically, you can see for these eigenfaces, you have red and black. So some of the entries are negative, some are positive, and that's how it works. So in PCA, we know the main thing is that these are all orthogonal to each other. They're all mutually orthogonal. And we know that, yes, if you want to construct this face, you take the mean plus this coefficient times that vector plus this coefficient times that vector and so on, add them all up, you get this. So non-negative matrix factorization works in a similar way. You don't have eigenvectors, but these are the building blocks. You don't subtract the mean. In this case, you need everything to be positive. So these are the building blocks, the dictionary elements, and these are the coefficients. And you can see here everything is positive. And as a result, the way that it works is fundamentally different. So this is what's called a parts-based decomposition. If you look closely, you can see like, oh, these are eyebrows. Or, I think like here's the bottom of the nose. You can actually see all the different parts. And you can see how those parts are combined to make the whole. Whereas with PCA, it's just a lot more confusing. You know that somehow these are all used, but somehow all those pluses and minuses are canceling out. But it's very difficult to see how that's happening because of all the pluses and minuses. Here, you can say, oh, okay, for this image, I basically took this with a high fraction, this with a high fraction, this, and I basically piece those together to make this. Okay, so it's sort of a different way of unpacking features into components. Okay, any questions on it? All right, one last slide for today, just to compare NMF and PCA. So a lot of similarities, but some differences. Both are low-rank approximations. As we said, NMF, you need a non-negative matrix to start. NMF obviously gives non-negative matrices, whereas PCA can have negative ones. NMF gives non-orthogonal matrices, whereas PCA gives orthogonal ones. NMF gives a lot of sparsity. When you look at these, you see tons of zeros. These are generally not sparse. NMF is not unique. There's actually different ways you can construct this, whereas PCA is unique. And these NMF solvers themselves are a little tricky. They can get stuck in local minima, but PCA, no problem with that. So here's a tutorial if you want to learn more about NMF. So, oh yeah, and I had a whole slide on this, I forgot. This is the Netflix problem that I was describing. So $1 million, 18,000 movies, 480,000 users, 100 million ratings, so only 1.2% of the ratings were available. And this is the cost function that you want to solve. You just sum over the known values. Okay, so that's it for today. Any last questions? All right, great. So we'll learn about a new topic which is related to k-means but a little bit more sophisticated next time. See you guys on Wednesday.